Hey there! Welcome to Lab Partner 101, your study buddy for making science and math simple. I'll walk you through tough concepts step by step so you never feel lost. Let's dive in. Welcome back to Lab Partner 101. Today we're going to talk about plate tectonics. The imperceptible and never-ending movement of these plates ties together many phenomena you've seen in the news and in textbooks. Massive quakes along California's fault lines, volcanoes flaring in Iceland, Mount Everest and the Himalayas inching ever higher, and a hidden mountain chain running down the middle of the Atlantic, deep below the ocean's surface. It's the idea that Earth's outer shell is broken into plates that move, collide, and stretch, slowly, but with consequences that build mountains, open oceans, and trigger quakes and tsunamis. Once you see it, the world map stops looking random. Coastlines, mountain belts, and volcano chains begin to make sense. Centuries before the modern theory of plate tectonics, some people noticed something odd about the world map. The continents looked like they might fit together. In 1596, mapmaker Abraham Ortelius suggested that the Americas had been torn away from Europe and Africa. In 1858, Antonio Snider Pellegrini even published drawings of the continents joined into a single landmass. The resemblance was striking, but scientists of the time simply couldn't accept that continents could move. The sticking point was mechanism. Rock sliding through rock seemed impossible. Instead, scientists leaned on other explanations. Vast land bridges that later sank beneath the sea, or the shrinking Earth idea, that as the planet cooled, it wrinkled like a drying apple to form mountains. Some even proposed an expanding Earth to explain the puzzle piece fit. Against this backdrop, the idea of whole continents drifting across the globe sounded like speculation. Then, in 1912, a German meteorologist named Alfred Wegener pulled the evidence together into a single argument. He showed how mountain ranges on opposite sides of the Atlantic line up, how fossils of the freshwater reptile Mesosaurus appear in both South America and Africa, and how ancient glacial scratches run in the same directions across now tropical continents. Wegener proposed that all of Earth's landmasses had once been joined in a supercontinent he called Pangaea, which later split apart and drifted into the positions we see today. Wegener's evidence was compelling, but his explanation for how continents moved was not. He suggested they might plow through ocean crust under forces like Earth's rotation. Physicists quickly dismissed this idea. The crust was far too rigid. To them, it was like trying to shove a car through a brick wall. Without a working mechanism, most geologists rejected continental drift as unscientific speculation. Wegener spent the rest of his career defending the theory, gathering more data on fossils, rocks, and climates that lined up across oceans. But the scientific community remained unconvinced. In 1930, while on an expedition in Greenland, Wegener died at just 50 years old, still certain the continents had drifted, but without the missing piece of how it all worked. That missing piece would surface decades later, not on land, but on the ocean floor. After World War II, navies had developed powerful sonar to hunt submarines. Scientists soon realized they could use the same technology to map the ocean floor. What they found changed geology forever. Instead of a flat, featureless plain, the seafloor was broken by a gigantic underwater mountain range, the Mid-Atlantic Ridge, stretching thousands of miles. This caught the attention of American geologist Harry Hess, who in the early 1960s suggested the seafloor itself was spreading. He proposed that molten material rose from deep inside Earth, creating new crust at mid-ocean ridges that slowly spread outward, before sinking back into the mantle at deep trenches. Hess called this seafloor spreading, the mechanism Wegener had been missing. But Hess's idea might never have been taken seriously without the work of Marie Tharp. Using thousands of sonar soundings, she painstakingly mapped the Atlantic seafloor and revealed a deep rift running down the center of the ridge. At first, her colleagues dismissed it. One even called her interpretation girl talk. But the data proved her right. Tharp's maps provided the visual proof of seafloor spreading and transformed Hess's proposal into a convincing theory. The final confirmation came from an unexpected source: Earth's magnetic field. The liquid metal outer core, spinning around the solid inner core, creates a powerful magnetic field, turning the planet into a dynamo. Every few 100,000 years, the field flips. North becomes south and vice versa. As molten rock hardened at the ridges, iron-rich minerals aligned with Earth's magnetic field, locking in the direction of that polarity like tape recordings. In 1963, British geologists Fred Vine and Drummond Matthews showed that these magnetic stripes were symmetrical on both sides of the ridge, perfect evidence that new crust was forming and spreading outward. By the late 1960s, the pieces all came together. Seafloor spreading, continental drift, and mountain building were part of one grand theory. The age of plate tectonics had arrived. Today we know Earth's surface is divided into about a dozen major plates and several smaller ones. The Pacific Plate, the North American Plate, the Eurasian Plate, the African Plate, and others. They're all in constant slow motion, gliding on the softer rock of the asthenosphere beneath. The lithosphere, Earth's cold and rigid outer shell of crust and upper mantle, floats on the asthenosphere, a hotter, more ductile layer that flows slowly over time. It's not molten liquid, but it's soft enough for the rigid plates above to creep across it, and colder, denser slabs of lithosphere can sink back into it at subduction zones. Tectonic plate boundaries are where we see the world's most dramatic geology. At divergent boundaries, plates pull apart, like along the mid-Atlantic ridge, where new ocean crust forms every day. At convergent boundaries, plates collide. Sometimes one plate dives beneath another in subduction, creating deep ocean trenches and fueling volcanic arcs, such as the Andes in South America or the Cascades in the Pacific Northwest. Other times, two continents collide head-on, buckling upward into massive mountain ranges like the Himalayas. At transform boundaries, plates slide past each other. The most famous example is California's San Andreas Fault, where the Pacific and North American plates grind side by side, storing stress that's released in earthquakes. These plate interactions explain why earthquakes, volcanoes, and mountain belts are clustered along plate boundaries. The so-called Ring of Fire around the Pacific is the most obvious example, a loop of subduction zones that produces most of the world's largest earthquakes and volcanic eruptions. But not all activity happens at boundaries. Some features form above hotspots, plumes of hot mantle rising in the middle of plates. The Hawaiian Islands are the best example. As the Pacific Plate drifts northwest, the relatively stationary hotspot stays fixed, punching out a chain of volcanoes that records the plate's motion. Yellowstone in North America and the Galapagos Islands are other hotspot systems shaped by the same process. If this video helped make plate tectonics click for you, hit that like button, subscribe, and share Lab Partner 101 with a friend who's studying too. And let me know in the comments what topics you'd like to see explained next. Your feedback drives this channel. With plate tectonics, Earth finally makes sense. The drifting continents Wegener envisioned, the spreading ridges mapped by Tharp, the magnetic stripes explained by Vine and Matthews, and the trenches studied by Hess. All of them connect into a single unifying theory. It explains Earth's past and helps us predict its future. From the breakup of ancient supercontinents to the earthquakes and eruptions still shaping our world.